Good day, my name is Richard and a warm welcome to Tutoring with Richard, where we cover the South African school syllabus and related topics. Today we're going to cover strength of materials in 6. The topic of this tutorial is thick cylinders, example 2.3. Let's get straight into it. Okay, first things first, we need to read our question. We're going to read our question. Okay. 2 hollow cylinders of the same material are shrunk together to form a compound cylinder. The intermediate pressure between the 2 cylinders is 20 megapascals when shrunk together. The inside diameter of the cylinder is 100 millimeters and the common diameter is 180 millimeters. That's the outside of one and the inside of another. That's the common diameter. The outside diameter of the outer cylinder is 280 millimeters. After the cylinders are shrunk together, an internal pressure of 120 megapascals is applied in the inner cylinder. Now, calculate the actual stresses, the radial and hoop stress, in the compound cylinder. Okay. Now, our solution. In this case, we first need to find the stresses due to shrinkage and the stresses due to internal pressure before we can add them and get the actual resultant stresses. It will also be a good idea to draw we're going to draw the graphs for each one and fill in the values for the stresses as they are calculated, as this will simplify addition at the end. Right, so first of all, this is basically our cylinder. That's basically our 2 cylinders. That's basically our 2 cylinders together. This is our 2 cylinders. This part there, that diameter is 180. This diameter, that's a diameter. Diameter here is 280. And the inside diameter is 100. Okay, that means its diameter. So, what we're basically doing is we're looking for all our stresses in this compound cylinder. Right, so how we do that is we draw our graphs. And our graphs look like this. Our first graph, there's going to be 3 of them, and we don't know what's going on in each of them yet. Okay, so first what we're going to do is go, that's the first one, and there goes the second one. Now, this is that's the inner and the outer. Next, going up top here, is our hoop stress. Now this, down the bottom here, is our radial stress. And this is also radial stress. Right, down here also our hoop stress. This is negative, that's positive. And that is hoop on the outer. Now we are going to fill in values as they come. So now the next graph looks like this. Right, so next graph, now this first graph is a shrinkage graph. The next graph is internal pressure. The next one is internal pressure. How internal pressure works is it goes like that, and then this goes like that. That is how an internal pressure graph works. So, what we are going to do now, our internal pressure. Our internal is 120, as I've said in the question. The internal pressure of the shrunk cylinders, the internal pressure of 120 is applied to the inner cylinder. So this is where the 120 comes from. Over here, at this point of the midpoint, so this is 100, 180, and 280. So at this point here, at that point up there, there's 20 as well. That is 20. That is 20 because that is what we are given. We are given that. The graphs first. Right, so we are given that. Now, we need to calculate. Now we equal the reason it's 3 lines is because we are doing 2 cylinders at the same time. And that's how the graph will look, because this is the inner cylinder, there's the outer cylinder. Inner cylinder, outer cylinder. Inner cylinder, outer cylinder. Right, so it'll all look like that. Now, what this one will look like, it'll look like that. That one will look like that. And this will look like that. Actually, that one's a little too high. There we go. Now, this is at 120. This is the pressure we start with. And it's plus, and that's minus. This is minus. Right, so what we have here is I've got all the values that have been given to us on these 2 graphs. So, let's get rid of this because this is unimportant. Now, what we need to realize is that we have the 20 megapascals. So, the radial stress is 20 at 180. 20 megapascals at 180. That's why it goes up and then carries on like that. So basically we've got to find, and now also we will have inside diameter of the inner cylinder inside of the inner is 100 millimeters. Common equals 180 millimeters. Then out of the outer equals 280. Now all these will be 100, 180, 280. 100, 180, and 280. Okay, these are how they all work. Now, these graphs will get values as we calculate. They will get values as we calculate. So, what we need to do first, after the cylinders are shrunk together, now we have an internal pressure of 120 megapascals. That's the highest it's going to go. Okay, and there's nothing else. Now we're going to use our LeMay's formula. We're going to use our LeMay formulas. So, in this case, R, I'm going to put my LeMay's formulas here. Right, I'm going to write them there, but just so we can keep, let's write them here so that we can keep track of them. Radial is equal to A plus B over D squared. For hoop, that's A minus B over D squared. Okay, quite simple formulas to remember. But what we will need is all the space possible. We will need all the space possible on this side of the board. And I might even go into the board there. So, what we're going to do now is calculate. We're going to determine A and B, because A and B can be determined by any of these three here, any of these three diameters. Now what we have is radials. We got radials at 0, at 100 and 180. And we also need a radial at 180, and we've got a radial at 280. So what we're going to do is get our radials from 100 and 180. So 0, our radial equals 0 equals A plus B over 0, 1 squared. Okay, 0, 1 squared equals A over 100 B. Because 1 over 0, 1 squared is 100. You put that in your calculator, 1 over 0, 1 squared is equal to 100. Over 0, 1 squared. Now, what we are going to do, is work out B. So, now B, A equals 100 B. So, we'll need to work out the resultant hoop and radial stress. So, we'll have to combine them later. So we're going to have to do two. We're going to have to do the shrinkage, then the internal pressure, and then the resultant. Right now we're ignoring internal pressure and we're doing the shrinkage. Right now we're ignoring the internal pressure and doing the shrinkage. So we're following the shrinkage graph. Okay, so now 20 times 10 to the 9 megapascals 10 to the 6 equals A plus B over 0,18 squared. Okay. It is equal to A plus 30,86 B. Minus 100. So, I've got 20 times 10 to the 6 equal minus 100 B plus 30,86 B. Okay, let's calculate. Minus 100 plus 30, x6 equals 69,14 B minus. So 20 times 10 to the 6 minus 69,14. It is minus equals minus 0,289 times 10 to the 6. Right. So, that's what we're going to do now. Next point, that is B. So, B equals minus 0,289 times 10 to the 6th power. Now, A is minus 100B. So, multiply that by minus 100. So, minus 100 times minus 0,289 times 10 to the 6. And we're left with 28,9. Okay? That's 28,9 times 10 to the 6th power. Alright, so next point. We want both radial and hoop stress. We just worked out A and B for now, but we want radial and hoop stress for shrinkage. Next we're going to do all this again for, next next we're going to do all this again for internal pressure. So, next step. Okay, first step is 100. Our hoop stress at 100. So, hoop at 100 is going to be A minus B over 0,1 squared. So, A is 28,9 times 10 to the 6 minus 0,289 times 10 to the 6 all over 0,1 squared. And it gives me an answer of 57,8. 57,8 megapascals. 57,8 megapascals. Right, so that will go at the top here. 57,8. Like I said, we'll be filling this in as we go along. Okay, this is for the inner cylinder. So we only need 100 and 180. So, hoop at 180 is 28,9 times 10 to the 6 minus 0,289 times 10 to the 6 all over 0,18 squared. Hoop at 180. It'll be the same for both. It'll be exactly the same for both. So, hoop at 180 will be 37,82 megapascal. 37,82 megapascals. That's our lowest over here. That's not our radial, that's our hoop. So it's 38, 37,82. That's at this point here. That's at that point there. I know it's not very clear, but that is our value at the top here, just below, just above these two arcs, just above those two arcs. Okay, next point. Now we're going to get the hoops, the radial. Now we're going to get the radial stress. Now we have to get A and B again. We have to get A and B again. We're still ignoring the outer sleeve. So, what we need to calculate now is 180 and 280. So, let's go. So we need to calculate A and B. We need to calculate A and B. So 280. So the radial at 280 equals 0, which will equal A plus B over 0,28 squared. So, what we have now is 1 over 0,28 squared. $12.76. So equals A equals minus 12.76. B. Okay. Now what we need to do is calculate 180. So radial at 180 is 20 times 10 to the 6 equals A plus B over 0,128 18 squared. Now this will be 30,86 A plus 30,86. Then we put A in, that's B. So 20 times 10 to the 6. Now A is minus 12,76. B plus 30,86B. And what we end up with, is we want B, so minus 12,76 plus 30,86. 18,1. 18,1 B. 20 times 10 to the 6 divided by 18,1 equals B. 20 times 10 to the 6 divided by 18,1. It is. Now B is positive 1,105 times 10 to the 6. Okay. Now we're going to look for A. So A is minus 12,76 multiplied by 1,105 times 10 to the 6. Minus 12,76 times 1,105 times 10 to the power 6. 14,1. So minus 14,1 times 10 to the 6. And this is also a negative. Negative times a negative. So, because these are radial stressors, so they will be negatives. Now we need the hoop stresses. And we get for 180 and 280. So that's this hoop stress here. The hoop stress at the top was the other one. So this is this bottom one now. Hoop stress for 180, hoop stress for 280. Okay, so minus 14,1 minus 1,1 over 5 times 10 to the 6 all over 0,18 squared. Right. Okay, this equals minus 48,21 megapascals. Minus 48,21 megapascals. Now 280. All I have to do is just change the 1 and the 180 to a 2. And that is times 10 to the 6 minus equals, the answer will change, obviously, because we've changed one variable, which will be minus 28,2 megapascals. Minus 28,2 megapascals. Right, so what have we learned? Is that this is minus 28,2 and this is minus 48,21. Alright, now we've just got to solve. Now all we have to do is solve a radial and a hoop stress problem for our internal. Now we're dealing with internal pressure. Okay. Now we're going to consider internal pressure. Now we're going to consider the second graph. So all we have there is 120. And this is our radial graph. Radial pressure, radial pressure. That is all we have. So, what we need to calculate is at 100 we have 120. So 120 times 10 to the 6 equals A plus B over 0,1 squared. So A, so we can't do that. So to get A, okay, we're going to substitute. It'll be 120 times 10 to the 6, A plus 100 B. Okay, so at 180 we do not have it at 0, but the graph runs through it to 280, and 280 is at 0. So 280 is at 0, so we will equal 0 equals radial at 280 equals A plus B over 0,28 squared. So, what we have here is A is equal to minus 1 over 0,28 squared. And that is minus 12,76 B. Okay. Now we combine the two. So we have 120 times 10 to the 6 equaling minus 112 minus 12, 76 B plus 100 B. Okay, so minus 12, 76 plus 100 equals 87,24 B. 120 times 10 to the 6 divided by 87,24, and that'll give us B. So what we need to do is say 120 times 10 to the power 6 divided by 87,24 equals it is a positive number. B is equal to 1, 376 times 10 to the power 6. So, now A, all we have to do is work out A. And A is minus 12 times 1,376 times 10 to the power 6. And A is minus 17,54 times 10 to the power 6. Okay. Now what we're going to do is work out the hoop stress. This radial stress is all given to us. So we are going to work out our hoop stresses. So, our hoop of 100 and 180, because that is the internal cylinder. Then we're going to work out the external cylinder after that. So, our hoop for 180, cylinder that's internal. We're doing this for internal pressure now. Right. Now, this will be quite simple to do. We can just go through all three and do it because it's one long graph. For internal pressure, it's one long graph. So wherever they lie, that is where they will be. So this is not a long one to do. It's not like we have to split it and redo every sum. It's just one compact graph. So we don't have to work out A and B again. We just have to work out that graph. Perfect. So what we need now what we will need now is the radial stress at 180. So radial at 180, which will equal minus 17,54 plus, because radial is always plus 1,376 times 10 to the power 6. This is also times 10 to the power 6 divided by 0,18 squared. Right, so minus 17,54 times 10 to the power 6 plus fraction 1,376 times 10 to the power 6, 0,18 squared. That is 20, now this is not hoop stress, this is radial, so it's 24,93 megapascals. That's common. This is common. That's a common theme. So, next thing we do is the hoop stress of each one. So, all we have to do is take this and minus. So, our hoop stresses. Now we take this. Right, so now we're going to get hoop stress at 180 internal pressure. So that is going to be minus 17,54 times 10 to the power 6 minus 1,376 times 10 to the power 6 all over 0,18 times power 2 minus 60,00,01 times 10 to the power 6. Okay. Now all we do is take this away, take that away, and we deal with 100. It was easier dealing with that. Now, hoop stress at 100, internal, minus 155,14 times 10 to the power 6. That gives us minus 155,14 times 10 to the power 6. Right, now all we have to do is just change it to 280. Now we just have to change this to 280. Minus 35,1 times 10 to the 6. Okay. Now, all we have to do now is put all our resultant forces together. All we have to do now is put all our resultant forces together. So what we have is 100. This is all going to be radials. The resultant radial stress, resultant radial, the resultant radials will be for 100 and will equal 0 plus 120 equals 120. For 180 will equal 20 plus 24,89. Right, as we did this, the radial for 180. This is combining our shrinkage of 20 with our internal pressure of 24,93. That's combining all our radials, then we will combine all our hoop stresses together. So this is our 180, so that is 44,89. This is all in megapascals. All of this is in megapascals. So then at 280, we have our radial, which was 0 plus 0 equals 0 megapascals. Because the radial, I'm going to explain this, because the radial here at 280 is 0, and the radial here at 280 is also 0. So look on both graphs and you'll actually see 0 plus 0 equals 0 megapascals. So I'm going to give you a chance to copy that. Now we're moving on to the hoop stresses. Now we're going to move on to hoop stresses for the inner diameter. And then we'll move on to hoop stresses for the outer diameter. Let's move on to hoop stresses for the inner diameter, then the outer diameter. So the inner diameter resultant hoop stress for the inner diameter 100 equals, right, let's look at this. At 100 it was 57,8. 57,8 plus, now this is over here, so at 100 it's all the way down here. So that is the hoop stress for 100, the outstanding hoop stress for the internal for 100 is minus 155,14. Minus 155,14. Alright, so this will equal minus equals minus 97,2 megapascals. Right, so 180. At 180, we have negative 48,21 at a hoop. So 180, we have at a hoop is minus 60,1. Plus minus 60,1. No, I have a bit here, this hoop stress, this is the right one. I'm actually at 37,82 positive. 37,82. Right. And this will equal 37,82 plus bracket minus 16,1 equals 22,28 megapascals. Alright, so what we're going to do next is now we're going to do the hoop stress for the outer shell. So, result resultant for the outer. Now this is 180 equals, now 180, I am at negative 48,21 plus, now inner, now the outer, yes, I'm correct. And it is minus 60,1. Minus 48,21 plus minus 60,1. Okay. 108,31 times megapascals. This is a negative, by the way. So, now the last thing to do is 280 equals, now at 280 our hoop stress was negative 28,2 and our final hoop stress is plus minus 35,1. So it equals minus 28,1, 28,2 plus 35,1 equals 63,3 megapascals. Okay, you are very, very unlikely to come across a question like this in the exam. They'll probably give you part of this type of question, or they will use a different question. They will probably give you a sleeve and a solid shaft. That's what they'd probably give you, a sleeve and a solid shaft. Other than that, they'll never give you a cylinder inside a cylinder, a sleeve inside a sleeve. They probably would never do something like this in the test. It is very unlikely because it just takes too long. As you can see, this took us quite a long time to do. So this will take up most of your exam time, especially if you're writing a 3-hour exam. This will take up at least an hour and a half of your exam. And then you have no time to write the rest of it. Okay. So if you found this tutorial helpful, please give it a like and subscribe. It costs you nothing, but it helps with the algorithm and helps the channel to grow. Positive feedback is most welcome. I enjoy reading your comments. Please use the comment section to let me know what topics you'd like me to cover in upcoming videos. Be at peace, be kind to each other, and remember, passing well is achievable. Have a great day. Looking forward to seeing you in the next video.